All right, so in space, three-dimensional forces systems, so we have a particle and we have forces that are arbitrarily in three different directions, for example. Here I'm going to just draw the axes x, y, and z like this. Then the situation, sum of all the forces equals 0 on this particle still holds. So this means the sum of the forces in the x direction, let's do it as a vector with components, plus the sum of the forces in the j direction plus the sum of the forces in the k direction all need to equal 0, which leads again to the situation where sum of our force components in the x direction equals 0, sum of our forces in the y direction equals 0, and sum of our forces now we have in a z direction equal 0. And let's do another example. Okay, this drawing's a little tricky, but so we have this point O that's suspended, non-moving in space, and it's being held up by a string C, or a line C to the ceiling here. And horizontally in the y direction and in the b direction there are springs that attach to the wall, and these forces hold this weight up of 162.2 kilograms. So I've gone ahead and drawn my axis system to originate at point O here, where all these meet. And these then are the units. So from O, we move 6 meters in the x direction. We move 6 meters in the x direction, let's see, this way. 4 meters in the y direction. And then 12 meters up in the z direction to get to point C. So this point has a coordinate with respect to O of, let's see, 4, 6, and then 12. Scratch that and reverse these. This is actually 6 in the x, 4 in the y. I said it right, but I wrote it down wrong. 6, 4, 12. Each of these springs has a constant of k equals 360 newtons per meter. And they're both the same. And originally, well, we'll mention that in a second. I guess we'll mention it right now. So if unstretched, the springs have a length, why did I do gamma? Have a length equal to 2 meters. I want to determine the stretch in each spring. They don't necessarily both have the same amount of stressing because they don't have the same amount of force, even though they have the same K value in each spring. Okay, well, we can take our same approach here and just get started. This is what we ought to do in any problem. Sum forces equals 0, and let's just find our forces that we can find here. So with a free body diagram, I'm going to have force down of 196.2 newtons. I'm going to have force in the x direction. I'll call it force B. I'm going to have a force in the y direction. Call it A. And then we have this force of OC, which is at an angle. So we've got this XY plane here. Just so we can orient where this is. Again, this is 6 meters. This distance, which is obviously not drawn to scale, is 4 meters. And the distance up is 12 meters. So we can locate all these points Cartesianly. Cartesianly, that word. So first we have FA. And that looks like it equals minus J times our force component in that direction. So force A times J. We'll go ahead and make that a minus. We have a force in the B direction, force component B. In the negative I direction, we have just this force equals to 196.2 newtons, and that's going to be negative also. A lot of negatives here. And then we have this force in OC. And let's use a direction vector to determine that. So we've got our component force in the OC with 6 6I plus 4J plus 12K. That's our direction vector divided by its magnitude, which equals square root of 196, or 14. So we've got 6 14s here, or better yet, this is 3/7 I, 4 14ths is plus 2/7 J, and 12 is 6/7 plus 6/7 K. So when we sum all these forces, we need to end up with 0. So this means if we sum our forces, our x components, we equal 0. So that's going to give us 3/7. Oh, I forgot to put our force in here, because we have to multiply our direction vector by our magnitude of our force. So 3/7 force in OC minus FB. That's an I component. So I'll circle the ones that I use so we can keep track of them. Okay, and Y we have some forces. I went ahead and changed colors, so we'll do all this in colors. So sum of 2/7 FOC, this one, minus FA, this one, and then minus this one, minus 196.2. And no, 196.2 is in the K direction, so that doesn't count here. And then for sum of forces in the Z direction equals 6/7 FOC, this guy. Now we subtract off this, minus 196.2 newtons. So we look at this, we see we have 3 simultaneous equations and 3 unknowns. So we can solve this. Your method of your choice to solve this. You could use Cramer's rule. You could set this up into a matrix and invert it. We're going to learn some other techniques later, or you can just solve these equations in terms of each other and substitute in each of the equations, each of the 3 equations, until you get your results. And here are those results. It's not quite our answer because the question asked us, so we found the forces in each of these members, but the question asked us determine the stretch in each spring. So how much is each spring elongated? And really, I'm just calling these B and A. So for each of these springs, we have force equals some delta times K equals some delta times our K value is constant 360 newtons per meter. So our first delta is force of A divided by K equals 65.4 divided by 360, and that'll be newtons divided by newtons per meter. Or 0.816 meters. Our delta in OB equals, of course, our force B over the same K equals 98.1 newtons over 360 newton per meter equals 0.2725. So this is delta OA, delta OB.